Hello, I'm Simon Lee. I'm a PhD student at the University of Reading in the UK, and this is some work which I've done with Jason Furtado at the University of Oklahoma and Andrew Charlton-Perez also at the University of Reading, exploring the relationship between North American wintertime weather regimes and the stratospheric polar vortex. So North America's climate is diverse because it straddles the subtropics to the Arctic and is influenced by variability from both the Atlantic and the Pacific, which can make describing the large-scale conditions on any given day quite challenging. And so there are several modes of variability which we can use to describe the weather. These range from the Pacific North American pattern, the North Atlantic oscillation, the Arctic oscillation, the East Pacific oscillation, and several others. And this can mean that we have to sort of use this zoo of indices. We have to talk about several different indices at once to get a clear picture of what's going on. But regimes offer a framework of sort of unifying all of this together into one or several patterns, which means that the weather on any given day can be described as one of these recurrent patterns. And that's a much more straightforward approach. So regimes are a predefined set of recurrent patterns which describe a large-scale anomalous flow pattern on any given day. Unlike EOFs, empirical orthogonal functions, they describe close to the full picture rather than just a fraction of the variance, such as you might expect from something like a leading EOF. And unlike EOFs, there's no orthogonality constraint, so the resultant patterns are more physically realistic and you might more like what you might see when looking at a forecast anomaly map. And regimes are intrinsically long-lasting, so they tend to have timescales varying from around 5 days to often several weeks. And this can provide potential information for extended range prediction and looking into the subseasonal time frame. But we're particularly interested in them from the perspective of stratosphere-troposphere coupling. So they're useful because we can diagnose regional variability during the stratospheric vortex states, and that gives you a little bit more information than just considering the annular mode, the northern annular mode across the whole hemisphere. We can also quantify the potential importance or lack thereof of the stratosphere for different regional weather types. And then we can use the combination of the persistence of the regimes, the persistence of the stratospheric anomalies, the anomalous circulations in the stratosphere have long timescales, and then an understanding of how the two interact to get longer-term, potentially useful information. So to diagnose regimes over North America, we take the ERA interim reanalysis and we take all days in December to March from 1979 to 2017, taking December to March because this is the period of largest stratospheric vortex variability. It's the period of time in which all major southern stratospheric warmings have been observed. And we look at the region 180 to 30 west, 20 to 80 north to consider all of the continent and the jet regions of both basins. And look at the linearly detrended 500 hectopascal geopotential height anomalies in this region, anomalies computed with respect to the daily climatology. And then we perform empirical orthogonal function decomposition of this data set and retain the leading 12 EOFs, which explain 80% of the variance in the data set. And then, after having done that, we perform k-means clustering with k set to be 4, based on a few previous studies which suggest that 4 is the correct number of regimes, a significant number of regimes to use over this region. And we perform the k-means clustering in the principal component space because it reduces the dimensionality to just 12 rather than the number of latitude and longitude grid points in this box, and also filters out those smaller scale noise because we've only retained 12 EOFs. And so we get 4 North American regimes, and in the end, the patterns are quite similar to Strauss et al. 2007, so we take their names for consistency. And what's shown here is the composite mean 500 hectopascal geopotential height anomalies for all the days assigned to these regimes over 1979 to 2017, and the percent of days in that time period assigned to each of the regimes. So first off, we have the Arctic high, which is essentially Greenland blocking. It's like a negative North Atlantic oscillation pattern. Interestingly, there's no significant anomaly in the North Pacific during this regime. In the Arctic low regime, it's quite similar to the negative PNA or negative North Pacific oscillation with this anomalous ridge in the Northeast Pacific and trough along the west coast. The The Alaskan Ridge regime is similar to the negative East Pacific oscillation, with this this dipole between the ridge and trough in the Northeast Pacific, and looks like a Rossby wave train emanating from the tropics and down toward into the Atlantic, which is similar to the tropical Northern Hemisphere pattern. The Pacific Trough, which is the most frequent regime, occurring on 29% of days, looks like a positive North Pacific oscillation and has similarities to positive PNA, with this anomalous trough centered on the Aleutian Islands. And then to diagnose how these regimes change based on the stratospheric vortex, we consider the 100 hectopascal 60 north zonal mean zonal wind. And the reason for choosing 100 is that this is a lower stratospheric level where anomalies are more likely to influence what's going on in the troposphere, rather than considering variability higher up in the stratosphere. And we look at the tercile categories of these of the 100 hectopascal winds based on the daily climatology. And then we compute the probability of occurrence depending on these tercile categories and the probability of the regime persisting into the next day. And it should be stated that whilst these are quite fairly instantaneous relationships, that because of the persistence timescale of circulation anomalies in the lower stratosphere, that longer-term useful information can be extracted from this. So the Arctic high regime is the one with the strongest relationship with the stratospheric vortex. It's around 7 times more likely to occur following a weak stratospheric vortex as strong. It's very unlikely during a strong stratospheric vortex, and it's 30% more likely to persist in a weakened stratospheric vortex versus a strong vortex. And it's the only regime with a significant change in its persistence likelihood. And then the Arctic low and Pacific trough regimes almost have an opposite sensitivity. They're more likely to occur in a stronger vortex, although the change in the probability across the tercile states is less than it is for the Arctic high. And then the Alaskan Ridge regime, and this is the interesting one, is equiprobable for all the tercile states of the vortex, which suggests that the stratospheric vortex, there's no statistical link between the strength of the lower stratospheric vortex and the occurrence of this regime. And that suggests that looking at the strength of the stratospheric vortex, it doesn't give you any useful information to determine whether or not this is likely to occur. So now we move from 100 hectopascals up to 10 hectopascals in the mid-stratosphere, which is the level at which major sudden stratospheric warming events are commonly defined, just to get an idea of how the vortex is behaving during each of these regimes. And shown here are the composite mean 10 hectopascal geopotential height anomalies for all days assigned to these regimes in era interim. And in the Arctic high regime, what we have is a significantly weakened stratospheric vortex with raised geopotential heights over the central Arctic, and this is consistent with what we might expect during a sudden stratospheric warming event, and also consistent with the fact that this regime tends to only occur when the stratospheric vortex is weakened. In the Arctic low, we have almost a mirror image, a mirror but opposite image of the Arctic high anomaly pattern with lower geopotential heights over the Arctic, indicative of a strengthened stratospheric vortex. Similar picture again for the Pacific trough, although there is a wave number 1 disturbance, but the lower geopotential heights over the Arctic again suggesting a strengthened stratospheric vortex. And then most interestingly, during the Alaskan Ridge regime, there is a significant wave number 2 disturbance with these anomalous ridges in the North Pacific and North Atlantic, and a cyclonic anomaly over North America. And this is indicative of an elongated vortex in the north-south direction, indicating some significant disruptions to the vortex. And it should also be noted that this cyclonic anomaly here overlies the cyclonic anomaly in the Alaskan Ridge regime over the Hudson Bay region. So this might be familiar to those of you who remember what was going on during the winter of 2014, which is infamously known as the polar vortex winter, so called because of the disruption to the stratospheric vortex and this elongation in the north-south direction and the extreme cold weather that occurred over northern North America. And actually the 10 hectopascal heights, according to NCEP-NCAR analysis, during January 2014 are very, very similar to our composite for the Alaskan Ridge across era interim. So this suggests potentially that changes to the stratospheric morphology So the elongation of the vortex might be important for driving this regime, or it's also possible that this regime is associated with driving disruption to the stratospheric vortex. But you don't see a signature in the 100 hectopascal zone mean zonal wind. And so, motivated by the severe cold weather that occurred during that polar vortex winter, we then look at the probability of severe cold air outbreaks, defined as 2-meter temperature anomalies below 1.5 standard deviations, for all the days assigned to these regimes in era interim. And what we find is that whilst the Arctic high is significantly associated with significantly raised probabilities of severe cold over northern Europe, there's only a slightly raised chance, a slight probability of severe cold across the US and parts of Canada, and instead that it's the Alaskan Ridge regime which is most strongly associated with severe cold air outbreaks over North America. And we see the same story when we look at the 2-meter temperature composites. These are anomalies with respect to the detrended 1979 to 2017. And we see that there are slightly cooler than normal conditions over the US during the Arctic high regime, but during the Alaskan Ridge regime, the majority of North America is around 3 to 5 Celsius cooler than normal. So this is the key takeaway, really, which is that the regime most strongly associated with these cold air outbreaks in North America is equally likely when the lower stratospheric vortex is strong as when it's weak, and that the same can't be said for Northern Europe, which means that if you are interested in knowing the likelihood of severe cold air outbreaks in North America, looking at the strength of the stratospheric vortex might not be really all that useful. So to summarize, we have 4 circulation regimes which can describe the large-scale patterns over North America during winter. The likelihood of these regimes differs depending on the strength of the lower stratospheric polar vortex. We have the Arctic high regime, which is similar to the negative NAO and 7 times more likely following a weak stratospheric vortex. We have the Arctic low and Pacific trough, which are more likely when the stratospheric vortex is neutral or strong. And then this Alaskan Ridge regime, which doesn't appear to be sensitive to the strength of the stratospheric vortex, although may be associated with some kind of change to the stratospheric vortex morphology and this barotropic anomaly over North America, which is similar to what happened in 2014. But this is the regime which has the greatest likelihood of severe cold weather over North America, even though it's not significantly more likely to occur when the polar vortex is weakened. And this suggests a different predictor and a different pathway for these coldest air outbreaks versus what happens in Northern Europe. And so we've got ongoing work to describe the relative importance of the stratosphere for getting accurate regime predictions, whether a more accurate stratospheric vortex forecast gives you a more accurate regime forecast. But for now, please do check out our paper in GRL, and thank you for listening.